Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Okay, so this problem asks us to find the ratio of the kinetic energy of an electron to the kinetic energy of a proton, given that the de Broglie wavelength of the electron is equal to the de Broglie wavelength of the proton, and we're working at speeds that are much less than the speed of light. All right, so let's consider what sort of things we need to know. Let's recall some equations that we've known in the past. We know that kinetic energy is going to be equal to 1/2 mv squared is our usual go-to on that. But we also want to remember what we learned in the momentum part, which is that kinetic energy can also be seen as the momentum squared over twice the mass of a particle. And we want to keep in mind that this formulation of kinetic energy is usually more handy when we're dealing with particle physics equations. So I'm going to leave that there for a minute. We also want to recall what the de Broglie wavelength is. And that says that the wavelength of a particle is going to be equal to the Planck constant h divided by the momentum of that particle. And here we see why the momentum formulation of kinetic energy is handy when we're dealing with particles. So let's explore this de Broglie wavelength situation with our given that the wavelength of the electron is equal to the wavelength of the proton. If that's true, then I can take this expression and think and say that the wavelength of the electron would be equal to h over the momentum of the electron, and that is going to be equal to the wavelength of the proton, which is going to be equal to h over the momentum of the proton. And h is just the Planck constant, so Planck constant over PE is equal to the Planck constant over PP. This implies that the momentum of the electron in our given condition must be equal to the momentum of the proton in our given condition. So instead of having two separate momenta, we're just going to deal with one momentum P that is the same. All right, so given that idea, let's go back to our kinetic energy formulation and the ratio that we're trying to explore here. So if we're looking for the ratio of the kinetic energy of the electron to the kinetic energy of the proton, then we're looking for, in fact, the ratio of p squared over 2 times the mass of the electron for the kinetic energy of the electron over p squared divided by 2 times the mass of a proton. And if we do some canceling now, we see that p squared over 2 appears in both parts here. So those are just going to cancel out. And what I'm left with is 1 over the mass of the electron over 1 over the mass of the proton. And if we simplify that complex fraction, we are left with this ratio of kinetic energy of the electron to the kinetic energy of the proton is simply equal to the ratio of the mass of the proton to the mass of the electron. And these are both given numbers, constants. So if we look up those numbers, we see that the mass of the proton is equal to 1.6726 times 10 to the minus 27 kilograms. and that's going to be divided by 9.11 times 10 to the minus 31 kilograms. And we see that that ratio is equal to approximately 1,840. So that's the answer to our question, to 3 sig figs, given the information in the textbook.